Okay, so this week we've got a learning intention to understand how colour depth affects file size. So there's a couple of bits in there that we're going to need to unpick. First of all is what is colour depth, and then how does it impact file size. So last week we looked at how binary was stored for a 1-bit image. So we looked at a 1-bit image and said, right, how do we know what colours are what in that image? And we looked at black and white. Now we saw that in each pixel of the bitmap, if we had 1 bit, that's either a 1 or a 0 in that pixel, and it could be coded that 1 is black and 2 is white, or the other way around. Or some of you did different colours, so it doesn't have to be black and white, it's just limited to 2 colours. And that was a 1-bit image. And that's a 1-bit image, remember, because there is 1 bit inside each pixel. So if in a 1-bit image you can have 2 colours, how many colours do you think you might have in a 2-bit image? And what is a 2-bit image? So we're going to look at that now. So in a 2-bit image, what we're talking about, what the difference is in each pixel, instead of there being 1 bit, there can be 2 bits. So for example, you could have a 1, 1 in your pixel. Okay, well that means you could also have a 0, 0, of course, and you can have a 1, 0 or a 0, 1. So there are 4 unique combinations when you've got 2 bits. So what that means is you have got 4 unique codes, and each of those codes can be added as a colour. So I've got 1, 1, 1, 0, 0, 1 and 0, 0. And you could assign any colours to those you wanted. There are 4 options. So for example, I could say I want green, blue, a black and a purple, or any other combination that you wanted. Okay, so you've got those colour combinations, but you can have any 4 colours you wanted. That's the maximum number of colours you'll get in a 2-bit image. So the number of combinations is 4, and that means that we can have 4 colours. Okay, so moving on, what about a 3-bit image? So thinking about what we're going to do here, you're going to have more options, aren't you? Because in each pixel, you can have 3. So I can have 1, 1, 1 as my starting one. Okay, now this is a little trickier. We're going to think a little bit more carefully when we do this. So I've got 1, 1, 1. So let's try and be systematic and logical. So I have 1, 1, 0, and then I can do 1, 0, 0. Okay, so that's a good row. Let's do the same for 0, 0, 0. And then I can have 0, 0, 1. And then I can have 0, 1, 1. Okay, is that all of my options? I don't think it is. I think there's more. So I can have 0, 1, 0. And that gives me 7 options. And what else could I have? Let's have a look. Are there any other combinations that I've missed? So could I have 1, 0, 1? I haven't got that yet. Okay. Are there any others I've missed? I don't believe there are. So these are all of your options. So you've got 1, 1, 1, 1, 1, 0, 100, or 1, 0, 0 really, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, and 1, 0, 1. All of those are unique. So how many have I got? How many options have I got? Well, I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 possible unique combinations. So in a 3-bit image, there are 3 binary bits per pixel, and that means that I can have 8 possible colours. And again, just like before, I could assign any colours I wanted to those colour combinations. So I might decide that in this one I want white and green and pink and let's have purple again. It's entirely up to the programmer what you're going to have. So you could still have white and black involved. We can have red. We'll have yellow, and for our 8th colour we will have cyan. There you go. Okay, so you can see that, but it could be any choice of 8 different colours. So that's a 3-bit image where we've got 3 bits of binary per pixel. That gives us 8 possible combinations. What you can't do is have 2 bits and 3 bits in the same image. You couldn't use, for example, what I couldn't do is have this as 1, 1. It's expecting 3 bits, so it has to have 3 bits. So 1, 1, 1 makes sense, whereas if you had a 1, 1 in a 3-bit image, it would break the image. It wouldn't load the image, it would be corrupted. Okay. So, how many colours do you think there would be in a 4-bit image? So a 4-bit image is going to have 4 bits per pixel. So how many combinations are there, and what does that mean for our number of colours? So in a 1-bit image we had 2 colours, in a 2-bit image we had 4 colours, in a 3-bit image we had 8 colours. So what do you think the prediction would be for a 4-bit image? If you look at the pattern there, every time we go up 1 bit, what happens to the number of colours? Okay, here's a task for you, and we'll just pause for a minute. In the back of your book, prove your answer. So if you think you know how many colours there are, see if you can find that many unique combinations using 4 bits. It's a tricky challenge, so you'll need a minute to have a go at this one. So back of your books, try and find each of the combinations to prove your number of colours correct. Okay, so we've got here a list of answers and how you can find it. So 1 bit is 2 colours, 2 bits, 4 colours, 3 bits, 8 colours. Hopefully you had a go at finding 16 colours. Did you find all the different combinations? Okay, so the pattern is obviously you are doubling the number of available colours each time you add an extra bit. So actually quite quickly, if we get to an 8-bit image, you've got 256 colours, which seems like quite a lot. But actually, most modern computer systems use a 24-bit image. So 24 bits in every pixel. So in a binary, that's, you could have all ones, and that's your 24 bits. That means you've got over 16 million possible combinations. So there are 16 million possible colours in an image, and that's on most modern systems. So actually, from very simple black and white ones and zeros, we're now very advanced in our technology in that we've got almost an unlimited number of colours to choose from. Different shades that are almost identical but slightly different can now be chosen because you've got that many bits per pixel. So let's think about resolution for a minute. And we talked a little bit about resolution right at the start of this topic, and we said, actually, the more pixels you have, the higher the resolution. That's what I said then. So to make that a bit more advanced, let's use the right terminology. So resolution is a measure of pixel density. How dense your pixels are, so how many pixels you've got in a certain space. And that's normally measured in dots per inch, or DPI. So on a website, you'd normally have a DPI of 72. So 72 is pretty good. You'll look at that on a screen and it'll look a high quality image. That means in one square of that image, you've got 72 across and 72 down. Okay, so there are 5,184 pixels per square inch. That's pretty high, but if you go and buy a glossy magazine or a book, they're printed in even higher resolution. They're often up to 300 or 600 dpi. So your resolution is just a measure of how many pixels you've got in a certain area. Okay, we talked about 4K, we talked about 1080 as being measures of your resolution. The higher that number, the more detailed your picture is going to be. But I said we're going to have to deal with two things. So we've just talked about color depth and how you can have more bits per pixel, and that's going to give you more options for colors. Let's talk about file size. So here I've got 2 images on this screen. You've got one image that's got 256 pixels as a DPI, so the dots per inch is 256, okay? In this one, I've got 64. Now you can see that the one on the left is much more detailed. The one on the right is pixelated. It's the same image, but there's a quality difference. They've got the same range of colours, so the colour depth is the same, but the resolution is different. which of these images will take up the most memory and explain why. So that's what I would like to look at. So do you think it's the one with 256 pixels or 64 pixels? And try and explain why you think it takes up more memory. Okay, so I don't just want, oh, I think it's this one. I want you to say, I think it is this one because, and there might be a little bit of maths you can do to prove it as well. I'll give you another chance to pause here to have a go at this on your line paper. Okay, so the crux of this one is the number of pixels that's going to be involved. If the images are the same space, but there's fewer pixels, that's going to take up fewer bits and bytes, and we'll even get into kilobytes and megabytes in this. Whereas if you've got more pixels, there's more information. So in both of these images, the color depth is the same. So let's say each pixel is taking up, it's an 8-bit image, or let's make it 10. Let's make our maths nice and easy. So let's say we've got every pixel is a 10-bit. So every pixel equals 10 bits. Okay. What does that mean? Well, there's very simple maths from here on in, because we go, right, if in my left-hand image there are 256 pixels, then all I've got to do to find out how many bits that is multiply it by how many bits there are in every pixel. So multiply by 10. So that's multiplied by 10, and we end up with 2,560 bits for that whole image. Okay. If I look at my other side, I know I've got 64 pixels. So same calculation because the color depth is the same. So 64 pixels times by 10, because there are 10 bits in every pixel, is going to equal 640 pixels. Okay, so immediately we can see that actually this one is 4 times that one. Okay, so that's going to take up that much more memory because you've got that much more binary to remember. So hopefully your answers show that. If it hasn't, can you just green pen that for me now? You'll just need to note down this and these calculations to show the difference. Okay. Right, so here's what I'd like you to do today. Here's our success criteria. So bronze is to understand that every pixel is coded using binary. So you could go back to your black and white and you could talk about your black and white images to show you've understood that. Explain what a bit is and how bit size is linked to color. So that's what we've done today. We've looked at color depth, and the more bits you have per pixel, the greater color depth you can have. Then explain how color depth is linked to file size. So that's thinking about the last slide, and actually how if you've got greater color depth, each pixel's got more binary in it, and therefore the file size is going to be larger. And finally, I want you to think about vector images. So that's a challenge that we'll come back to next week. So we haven't talked about vector images yet. But the task you're going to do is you're going to write an explanation text about how binary stores images in bitmaps. Just move me out of the way. So this is a cold writing task. We haven't planned for this task. We'll do that. We'll do a plan next week, and we'll look at what we can add in for a hot writing task in the future. But for today, I just want you to take the knowledge you've got so far from this unit and do your best to write an explanation text about how binary stores images in bitmaps. That's essentially the title. So you can think of this almost as your title of your explanation text, is how binary stores images in bitmaps. Okay, I want you to do that on line paper, and I want it stuck in your books with the date, with the LI, please. Okay, best of luck, and I look forward to seeing them.